With a 49-to-1 transformer, does it make a difference whether the positive is connected to the tap or to the end of the winding? In this video, we will test that premise. Does it make a difference? In the previous video, I had the tap connected to the ground. In this video, I have the tap connected to the positive or the center conductor. Will it make a difference? Watch to the end to find out. This is a follow-up to the last video. In the last video, when I did my test, I had the tap connected to the ground connector on both of these. I've had to go in and reverse these connections as well. The tap is now connected to the center conductor of the coax, the SO239, and the ground is connected both to the shield here and also over here to the ground for the antenna. This is where you'd put your counterpoise or your radial. Will it make a difference in the test? We're going to connect up to the NanoVNA and we will rerun the test and we'll rerun our analysis. Okay, we've got our NanoVNA set up and connected to our test rig here. We've got the positive going to the tap on the auto transformer. We've got the negative going to the end of that winding. We've got the other end of that winding coming out the antenna, connected here to the second transformer, and then that signal will be coming through this transformer back to the NanoVNA on port 2. We still have our 100 picofarad TDK capacitor here, and we've got the tap coming from the transformer to the center conductor of the coax. So these are all in the correct polarity now, and we're going to go through our tests using the same frequencies and bands that we did in our previous test to see whether it makes a difference, how the polarity is on these transformers. So let's get into the NanoVNA and run those tests. Okay, we're going to take the measurements just like we did last time on all the bands and these frequencies. These are the same frequencies we've used on the previous test. We're going to measure using the back-to-back method, where the signal's going through both of the transformers and back. So we'll write that down here, then we'll divide it by 2 to get the single transformer insertion loss here, and then later we'll put it into the spreadsheet to do our analysis on the efficiency. So let's start with 1.797. All right, there's 1.797, and we're reading 1.7, negative 1.7. And that comes out to a negative 0.85. Negative 0.85 through a single UnUn. So let's go to 3.827 for our 80 meter reading. There's 3.827. Let it stabilize for a second. And that's negative 1.33. So that'll be negative 0.665. Let's go on up to 7.235. There's 7.235, and the reading here is negative 1.27. So that's 0.685. Sorry, that's 0.35. Let's go on up to 20 meters, 14.267. There's 14.267, that's negative 1.33, and again that's 0.665. Going up to 17 meters, 18.110, that's negative 1.32, bouncing around a little bit, so that's negative 0.66. 15 meters, 21,300, negative 1.27, and that's again negative 0.635. Go to 12 meters, 24.925. 24.925 is negative 1.38. 1.38. So that's -6, 9. And going up to 10 meters, 28.332. There's 28.332, and that's -1.54. -1.54, so that's -7, 7. All right, we'll put these numbers into our spreadsheet. We'll calculate our insertion loss. Well, this is the insertion loss here. We'll calculate our efficiency and see how the measurement on this setup compares with what we did when I had the leads reversed in the last video. This is the way it should be connected because it's an auto transformer. Negative should be on one end of the winding, which is here, and then positive, or the antenna, should be on the other end of the winding. And the tap is where our positive should be for our center conductor on our coax. And that's what we just got through testing. So let's put these numbers into the spreadsheet and come back and talk about them. As we saw in our last video, this is the tapped winding versus the twisted winding, and this is where the first two turns of the winding are both primary and secondary twisted together. And the tapped winding is where you have one continuous winding, but you tap it at the second turn, and that's where your connection is supposed to be made for your center conductor of your coax. And this is the results that we had last week, and the only thing I did here is I put this title on here so we can know which one we're talking about. This is the one we did in our previous video. The polarity was reversed. Auto transformer, you have ground on one end and your antenna at the other, and then your tap is in between those two, where you would put your center conductor of your coax. Well, I had my center conductor and my ground reversed. I had the center conductor on the end of the winding, and I had the ground on the tap at turn 2. And for an auto transformer, that's not correct. On an auto transformer, the ground needs to be on one end and your antenna on the other. So these are the readings that we got last week, and now I want to show and compare the readings we got this week on what's called the correct polarity. And what we did here, like I showed previously, here the positive goes to the center tap. The negative goes to the end of the winding. And that's the way it's supposed to be connected for an auto transformer. And here we've got the ground coming over to the other ground on the other transformer. And just to show that here we did the same thing, you see the tap right there, and that's going to the center conductor of the SO239. And the end of the winding here goes to the shield. It's also connected via this wire right here. It's connected up to the ground, where your ground or your counterpoise or your reflector is for your antenna. So this is the correct polarity for an auto transformer. Now, we see some changes here. The insertion loss for the correct polarity actually has gone up a little bit across the bands. It was lower on the 80 meter band. It was lower on the 40 meter band. But here on the 20 meter band, it went up by 2.5%. So you got 2.5% more insertion loss with the correct polarity than we did with the reverse polarity. And also here in the 17 meter band, that's another 2.7% insertion loss higher on the correct polarity than we had on the reverse polarity. And also here on 15 meter, it is a difference of 1.8% higher insertion loss with the correct polarity. And it's 2% higher down here on the 12 meter band, and it's what is that, 1.3% higher down on the 10 meter. So with the correct polarity, with this functioning as an auto transformer, the insertion loss averages a little higher than it did on the reverse polarity. And why is that? When this one was connected in reverse polarity, when the ground was on the center tap here on turn 2, that means your primary were these first two windings between this point here and the tap. That would have been your primary. So you had 2 turns on your primary, and then this should be 12 turns over here because it's 14 turns total. So you had a 2 to 12 ratio, so it was no longer a 49-to-1. So that made a difference in the resistance, what it was converting it to, and I'll have to get into the formula and show what that was doing, but that was not a 49-to-1 transformer when the ground was connected here, because that would have been a 2-turn primary and a 12-turn secondary. We'll have to go over that in more detail. And since they were both the same, we still got our 50 ohms on each one, because whatever this one was converting here, this one was converting back here. So that's the reason the readings look so good and so reasonable, but the resistance that this was actually tuned for would not have been in the 2,450 or 2,500 ohm range. And we'll get into that formula here in just a minute. Okay, we're going to have to get a little deeper in the weeds than I'd originally intended to, but hopefully this will help explain why it makes a difference where these leads are connected. This diagram represents the original configuration where I had the ground connected to the second tap on the transformer. I had the center of the coax connected to the bottom winding on the transformer, and of course the antenna connected here. But what this does is when you have the ground here, it isolates these 2 turns from the rest of the windings on the transformer. So what it turns it into is a 2-turn primary and a 12-turn secondary, because there's a total of 14 turns here. Well, that's not an auto transformer, and it doesn't give us the correct ratio. We're looking for a 49-to-1 ratio between our equipment, our radio, and our antenna, because antenna is going to be approximately 2,450 ohms. Well, with this particular transformer, that does not bring this down in the range of 50 ohms, which is what we're looking for. This should be around 50 ohms, plus or minus. And it varies with frequency, because this reacts to different frequencies. This is not a DC component. This is for AC, and it's going to react at different frequencies because you have an LC circuit, an inductor and a capacitor, and it's going to react at different frequencies, so the impedance is going to change. So what did this do? What did this configuration do to our matching? Well, to figure that out, we'll go through here. S is going to stand for secondary, the number of secondary turns we have. P is primary. And to determine the ratio of your transformer, you square the secondary and divide it by the square of the primary. Well, when we had 12 turns here, and we had 2 turns here, you square that, you've got 144 divided by 4, which equals 36. Well, 36 into 2,450 doesn't come out to a workable impedance for our radio. So if we divide 2,450 by 36, that comes out to 68 ohms, which is what we see here. Antenna impedance 2450, which is the approximation of the antenna impedance, but at this transformer ratio, or would give us 68 ohms or thereabouts. And that's a little bit high on average for our impedance matching transformer. So this is the reason why this particular setup will not work, is because this transformer, this with the ground being here, it isolates these 2 turns as a primary and these 12 turns as a secondary, and which gives us the 36:1 ratio. So let's look over here at how it is currently set up, where we have, this is the center conductor connection and this is the ground connection. The ground is connected to the end of the 14 turns, and the center conductor is connected to the tap that's on the second turn. This is a true auto transformer, because the main difference between a transformer and an auto transformer is that auto transformer, one end of the winding is connected to ground. So let's look here now at what we have. We have the same 14 turns with one end of the winding connected to ground, the other end of the winding connected to the antenna. A total of 14 turns. And then at the second turn, we have where our center coax conductor is connected. So we've got a 14 turn secondary, all 14 turns, and a 2-turn primary. Well, using the same formula we did, we square the number of secondary turns and the number of primary turns and divide the primary into the secondary. We get 14 squared divided by 2 squared, which is 196 divided by 4, which equals 49, 49:1. And with an antenna impedance of around 2450 divided by 49, that comes out to 50 ohms. And that's what we need, and that's what our radio needs in order to function properly. So that's the main difference. And you might say, well, why did the test results show such a good insertion loss? Well, the test results did not take into account the antenna impedance. Since we had both of these connected back to back and they were theoretically identical, it's going to negate any resistance. It's going to step it up the same through this transformer, and it's going to step it down the same through the other transformer while we were testing. So that's the reason we got such good test results. But in real life, had we connected this to an antenna load of approximately 2450 ohms, our SWR would have been extremely high, because it would have shown us a 68 ohm match instead of a 50 ohm match. And of course, even this 50 ohm is going to vary across the different bands that we're going to be operating on, because again, this is an LC circuit. We've got an inductor and a capacitor, and it's going to be resonant at one particular frequency or a narrow band of frequencies, and the rest of them are not going to be resonant. But on the average, this is going to be in the 50 ohm range, and that's what we're shooting for, and that's what we need. Where the ground and the center coax is connected makes the difference, because it's how it treats the windings here, and the windings determine what our ratio is of the matching transformer. Hopefully that's helped. Hopefully it hasn't muddied the waters. Lesson learned for me. Hopefully you've learned something from it as well. The results are, for an auto transformer, this has a lot less insertion loss than the twisted. Here's the twisted, where it went from 14.9 to 14.2, 13.7 to 13.6, 13.3. That one's a little higher, but you see it's flatter across the band here. Same here, that's only 0.1% insertion loss difference, where that one was 0.9 or 0.89. Same here, we had a lower by 2.06 insertion loss. And here at 12 meters, we had 4.8% less insertion loss, so it's better. And here at the 10 meter band, we had 10.22% less insertion loss. We see just a little difference here between the two different types of windings, but overall this is a vast improvement over this one here. The insertion losses here versus the insertion losses here. So hope this cleared things up a little bit. The way we built the transformer in our previous video, the build was correct. There's nothing wrong with the build. It's when I came down to testing it where I reversed the polarity of them was the only issue. The actual build was correct. This is the correct orientation. These are the correct ways to connect it up, where the positive goes to the tap and the ground goes to the end of the windings. And that's the way you should do it for an auto transformer. Hope you enjoyed it. We'll see you next time. This is Kilo Mike 4 Zulu Kilo Bravo. Have a blessed day.